So today I'm going to show you how to use the vector fields MATLAB code that we did in class to adapt it for problems on the homework. So basically how to use it to find vector fields of different equations, and then how to adapt the Euler's method section so that we can actually plot solutions to a different equation. And this might also be useful for the projects if your project involves finding vector fields. So if there's still questions about it after this video, please let me know and we can talk about what to do. So right now I just have the vector field MATLAB file up. What I'm going to do first is I'm going to copy this first section into a new file because I don't want to, if I make any mistakes, I don't want to have ruined my original code. I've done that plenty of times and have had to, figure out what I changed to make things work again. So for now, I'm just copying it over so that I still have an original working code if things go completely wrong. So we're looking at question, I think it's 8.2. Yeah, 8.2, number 13. So it says, use your numerical solver to draw the direction field, which is the vector field, for the given planar autonomous system, and then superimpose solution trajectories for several initial conditions of your choice. So we're going to focus on that first part right now, and then I'll transition to that second part. So we're just going to draw the vector field for the given planar system. So before I start doing that, what I'm going to do is I'm going to get rid of some of this extra stuff that we don't care about. Since my equations are different, these variables, there's no A, B, and C or D in this problem. I'm going to get rid of that. I'm going to, let's see, is there anything else? No. No, I'm gonna just leave this as is now. I guess this isn't gonna be calculating the vector field of the Lotka-Volterra model, but of a system. So now I'm going to go step by step with how we're going to change the code so that we can do at least question 13, and then hopefully if you watch this video, you can make the appropriate changes for question 15. So recall in class that what this code does is first it defines a mesh. So it's going to take our two-dimensional space and it's going to pick points, basically divide it up into little sections and denote points on that so that we essentially have a grid. And that grid is going to have start at 0 and go to 120 because that's what it was when we were looking at the predator-prey model. And for that grid, it was a spacing of 5 for every point. And at each one of those points, we're going to calculate the tangent field, the vector field, so the tangent at each point. And then it's going to plot all those vectors using this quiver function. Now, since we're doing a different equation than we did in class, then this max and this min value might not make any sense for what we're plotting. So we have to think a little bit about what our equations are telling us, and then determine what might be a good max and minimum like for our mesh. For the predator-prey model, it didn't make sense for anything to be negative because what is negative foxes and what is negative rabbits? That doesn't make any sense. So we started at 0, but that's not going to be the case for this. So let's switch over to look at what these equations are, and then we'll come back to the code. And when I look at these equations, I can think about, well, when does our equation do something interesting? So our equations for this case are theta prime equals omega, and omega prime equals minus sine of theta. So for theta prime equals omega, it's really hard to say when something interesting happens. That's basically, if we plotted that, that might look like just a line, y equals x. It tells me that when omega increases, theta prime increases. However, what we're going to focus on here is this sine function, because we know that sine goes between 0 and, -1 and 1. And when we plot our sine function, we know it ends up looking something like this. And basically, we know also that for I guess negative sine theta, I didn't plot negative sine here. I just plotted regular sine, but just imagine it flipped if you want. But we know that that for one period of our function, this goes between 0 and pi is about 3.14. So we might take a guess and say that maybe we care about mesh something that's closer to, -3 to 3, -5 to 5. It's really up to you what you choose here, but that's going to be very different than the 0 to 120 I had before. And in the y-axis, we might care about something that's -1 to 1, or maybe bigger than that. The way our code works is it makes a square. It doesn't make a rectangle. So I'm going to use my x-axis as the limiting factor, because more interesting things are happening in the x-axis than the y. So what I'm going to say is, let's say we want our grid, our vector field, to go from 10, -10 to 10. So it's going to go from that in both directions. And I don't know, maybe having a vector at every 1 unit might be too much. So let's say we have a vector at every 2 units. I don't know if it's going to look like something like this, but just kind of as an example. Okay, so let's go back to our code and see how we can make that change. All right. So going back to this min and max, we decided that maybe -10 would be good for our minimum, and maybe 10 would be good for our maximum. And for the spacing right now, I'm going to say that 2. We can always replot this and change it if we feel like it's, too sparse. So now we're actually going to go and look at this for loop, or this nested for loop here, which now goes through every point on that mesh, and calculates what the x component and the y component are of our tangent vectors are. However, we have this issue here, and this is because originally the minimum started at 0. So what this code did was it started at 0 and it went a certain number of steps that were equal to our maximum grid size divided by the spacing, and that it would give us how many steps to actually calculate those points. Since we're no longer starting at minimum equals 0, I won't get enough points if I leave it as is. So what I'm going to do is I'm going to change the number of points that I'm going to do this calculation as maximum minus minimum divided by the spacing. So instead of going from, say, 0 to 10 divided by the spacing, would get me, our spacing is 2, that would get me 5 points. What this is doing is it's saying, well, take the minimum, which is -10, subtract it from the maximum. So now I have a range of 20, divide that by the spacing. So then I'll have 10 points, which makes more sense with what we're trying to do with our grid. So it would have worked if I had minimum versus maximum, or sorry, maximum versus minimum with my minimum equals 0 before, but since it wasn't necessary at the time, I didn't think to do it. But if you make this change, you should be good no matter then what your minimum and maximum end up being. Okay, so now we're going to go back to our actual vector equations and change what's being calculated here. So u of I, like u of ij is going to be the tangent vector in the x direction at the ijth point. And v of ij is going to be the tangent vector in the y direction at the ijth point. So I'm going to switch back to my tablet to write some things down for a moment. Okay. So we can get a really clear idea of what's going on here. So let me, I'm going to just clean this plot up, make it kind of look a lot more like what's happening in my code. So if I have 10 and I have -10, and we have -10 and 10, and we said we're doing a spacing of 2, so that's 0, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, great. So what this is doing now is it's saying that I'm going to take all of these points and I'm going to just fill up the points for one coordinate right now, so we don't have a million dots. But so these points are x of, this is going to be, these points are going to be my, I guess, x of ij and y of ij, where x is going to be the x-axis and y is going to be the y-axis. But we know that for our set of differential equations that our x-axis is theta and our y-axis is omega. So if I were to calculate the vector at this point, so if this is 2, 2, I'm going to say that is 2, 2. What, if you recall in class, what we're going to do for that, if we do that sort of calculation by hand, is that we take our theta prime and our omega prime. So that's the vector that we're calculating, and that's going to be omega and sine of theta, and I'm going to plug in theta equals 2 and omega equals 2. So omega is 2 here and sine of 2, and I'm going to calculate what that vector is. So essentially, what we're seeing here is that the top of this vector is going to be the uij in in our code, and the bottom is going to be Vij. So when our code calculated Uij, what we're going to do is we're going to say, well, where in our mesh and what is happening in our equation. So our equation here is just omega for Uij. So that on our mesh is Xij. And for Vij, so that's the y direction of our tangent vector, our equation tells us it's going to be minus sine of, I just realized I messed this up, so I'm going to backtrack in a moment, but so X is going to be associated with theta, and omega is associated with y. So we have sine of theta here. So this is going to be negative sine of xij, which means that for this one, which was omega, omega is associated with y. This is going to be yij. So that's how we're going to change our code. Let's go back and see what that ends up looking like. So if I switch back to my desktop, I'm going to change the equations here, get rid of the predator-prey model because we are not doing that right now. And we said that Uij is going to be our omega, so it's going to take yi comma j, and our Vij is going to be minus sine of theta, which is x of I comma j. Oops. If I typed things, it would be good. And I'm missing one parenthesis here. Great. So the last thing I'm going to change is I have these lines where I can set the length of my x and y axes. This is independent of where I calculate my mesh. So I can actually do a calculation for my mesh between negative 10 and 10, and I can still plot outside of that area, or I could just focus really close in. So I'm gonna, for now, just change this to be whatever my minimum is to my maximum. And we can change that as we see fit. If we realize that, we did too many calculations and we actually only want to focus on a certain part, we can use those lines to change it. So now I'm going to run this and hope I didn't forget anything. Let's run that. So looks good. So our plot came up. It's on the other screen, but I just dragged it over. And we see that we have plotted between negative 10 and 10 in both directions. So that's great. And we see that we can really see what's going on here in terms of our vector. If we had it, too far out, we would still see something, but it might be a little bit hard to see the details here. And we can see here that if we think about our differential equation and our system and what it's doing, we can see that in the we have sort of this increase in vector on our y-axis here because of this first line. So because of that, theta prime equals omega, it's telling us, well, as we change omega, as we go up the y-axis, our vector in the x direction is now getting larger, and we can see these vectors getting larger as I'm moving up in the y direction. And we can see in the x direction something that to me feels a bit sinusoidal. We see that there's this up and down motion. So I'm feeling very confident with this sort of vector field right now. It makes sense to me. It might take a while to get a good feel for these things, but at least this I personally am happy with. So the next part of So I guess if you've done these changes so far, and then you're looking at question number 15, you would probably only really want to change these two lines here and make sure you're fixing the equation to match the equation in the book. You might have to play a little bit about the plotting size, but otherwise that should be the only thing you really need to change here. So the next part of this is superimpose solution trajectories for several initial conditions of your choice. So if we go back to the vector fields code from class, I'm going to copy that second part of the code because this is where we calculated our solution curves. And I'm going to just copy that down here, and we're going to make changes similarly that to like we did in the first part. First, I'm going to get rid of some unnecessary things. So I'm getting rid of these parameters because we don't need them. These two lines at the bottom I had commented out because I was doing them for something else. So I'm just going to get rid of them because they're not being accessed anyway. So first, what I'm going to do is I want to actually change F and S because I always confuse them with when I'm thinking about foxes and rabbits anyway, but I'm going to make them what the model is. So I'm going to say on our x-axis we had theta. So I'm going to change this to theta. Which I'll spell correctly. And notice when I start typing this in, MATLAB will tell you press Shift Enter to rename 6 instances of F to theta. And that's going to be nice because I don't have to forget if I forgot to change something else later on, I might have a problem. So I'm going to press Shift and Enter. And notice how all those F's have changed now to theta. And I'm going to do the same thing for omega so that I can keep straight what's happening here, not omega, omega. So Shift and Enter. Right. Okay. So before I start talking about initial conditions, I'm going to go and change the section on the Euler's method so that we can make sure we're doing the calculations correctly. So if we call from 2 weeks ago, maybe, the Euler's method, what it's going to do is it's going to calculate the next value in my differential equation by taking the current value, and then it basically calculates a line. So I'm using this tangent times my step size. My step size here is pretty small, 0.005. That should be fine. But now what I'm going to do is I'm going to put in what my differential equation actually is here. So what I'm going to do is for theta prime, we had omega of t at the whatever current t value. We're just calculating by finding out what omega t is, and then for omega prime we have minus sine of theta of t, and I think that's enough parentheses. So MATLAB will tell you by having some red squigglies if something doesn't look right. Sometimes they can be ignored. So right now I'm just kind of ignoring those. But when I didn't have enough, this semicolon here was red because it was telling me like, oh, there's a mistake there. So now I have the appropriate number of brackets. Okay, so this tells me that I'm going to hold on. I'm going to keep this plot because I want to superimpose my trajectories. And then I want to plot theta versus omega. But before I plot, we're going to talk about several different initial conditions. So the initial conditions of 40 and 20 don't make sense for this model. That's 40 and 20 are even outside of our our domain and range here. So what we're going to do is we're going to just pick coordinates that are somewhere in this visual. You can pick anything. I might start out by picking, let's see, x equals 6 and y equals -4. So theta equals 6 and omega equals -4. And now I'm going to just run this section. I don't need to run the whole thing because I already ran the first part. So I'm going to just run this section and hope I didn't forget to make any other changes. Didn't seem to plot. It did run. Didn't seem to plot. So it looks like I might have forgotten. Oh, no, it did plot. It just took a moment. So we see this orange curve here where it's starting at my initial condition, and Euler's method is just calculating that solution forward in time, and then it plots it. So we can see that it follows our vector field pretty nicely. I made the lines thicker on my vector field so that they'd show up better when sharing video. That might be a similar thing that we want to do for plotting here. I mean, you don't have to, but if you do want to, let me just check quickly what the line was. Yeah, it's so if you do want to change the thickness of your curve, what we're going to do is we're going to go to this plot theta comma omega, add another comma there, and in single quotes, write line width where L is capitalized and W is capitalized, have another comma, and then pick a number. So I think it starts out as 1. So you can try 2, you can try 3, et cetera, et cetera. So for this next one, I'm going to plot a thicker line. So maybe it'll be a little bit clearer. So let's see what happens if we pick a different sort of initial condition. So what I'm going to do here is I'm going to go back to my theta 1 and omega 1. So basically this is, the first point in our calculations for Euler's method. I'm going to pick, let's say, this is -8, 0. I'm going to pick right there. So theta is -8, and omega is 0. I want that to go away so we can actually see what happens. And then I'm going to run section. And see, so we get a different sort of initial condition here, and we can see the line is thicker because I made the line width thicker. So notice how if we think about qualitatively what these two solutions are doing, this one here is just going off to negative infinity in the x direction, in the x direction, and in the y direction it's just oscillating back and forth. For this initial condition, it's just oscillating in both directions, so it's making a circle. So for this, we just want to pick a bunch of different points. You might want to see, well, what happens if I try to find at what point do I no longer get circles. So maybe if I, instead of having -8, 0, maybe I'm going to have -8 and I'm going to move up to like 1. Let's see what happens if my initial condition starts there. So we have a slightly thicker circle here. It kind of looks like an eye. And maybe I want to see what happens at 1.5. Oh, now I no longer have a circle. So it looks like if my initial condition is changed slowly going up, at some point I'm going to have, these concentric circles. But if I make it too high, I end up getting this wave solution instead. So that I think is just like a pretty cool thing to show that there's different sort of dynamics here for this problem. I mean, it just says several initial conditions, so you can plot a few more if you like. You could try different ones than I did and see if there's anything else that happens. But that's all you have to do for the problem. If you are submitting this and you want to save this image, you could go to either File, Save As. So I recommend if you do save as, you save as a PDF or a PNG. So right now you'll see it as .fig, which is something that MATLAB reads and can modify, but we can just save it as a PDF or a PNG. I'll do a PDF and say something like 8.2. This is number 13, just so I know what that is, and save that and include that with your homework. So if hopefully this was helpful, if there's any other questions about using MATLAB in general, I know a lot of different things, maybe some specific things I might need to think about a little bit, but please feel free to ask. If you had issues, if you tried to follow along with this video and still had issues or have a question of like why I did a certain thing, please don't hesitate to ask. If you're trying to, change Euler's method and calculating the vector field at different points for problem 15 and you're still having some difficulty, then just shoot me an email.